Okay, so empirical and molecular formula, we are an application of, is an application of calculating moles, but not the really sort of tricky questions like with entities and stuff, just grams to moles. So even if you haven't had a chance to do much of the homework, that you should be okay. And then hopefully you'll see too how, or why, I guess, we calculate the amount in moles, how we can apply it to other things, like how useful it is, okay? So we, this year, have been looking at not skipping elements. Why do some compounds have weird formulas that don't follow the crisscross rule and things like that? So again, this is a quantitative way that you can figure out the formula, like literally the chemical formula. How many atoms of each type are in a molecule? So we're going to do empirical, which is the simplest. Like as in the most reduced. And then we're going to do molecular, which is the actual number of atoms. And the reason, empirical formula you can do for ionic compounds, and it should relate to what you get when you crisscross, right? Because we always reduce those. But then when we do the other type called molecular formula, it really is more specific for molecules, because when you have sharing, then you can have weird things start to happen. And you'll even see molecules that have more than 2 elements in them, right? So how do we get those formulas? This is a mathematical way to figure that out. And then what we're going to do tomorrow morning is looking at formula of a hydrate. So that's an ionic compound, but you have waters on there. How do we figure out how many waters go? Because that's not the crisscross rule, right? So this is trying to, a quantitative way to try to deal with the exceptions. So we're not going to skip the columns and stuff like that anymore, okay? So we're going to do the simplest. So the easiest thing to do here is an example, because none of this math is technically new. We're going to take grams, divide by the molecular weight, and find moles, okay? So here we're given percentages. So you could be given percentages or grams. When you're given percents, we're just going to assume a 100-gram sample, because no matter what the sample is, if 2.2% of it is hydrogen to 26.7% carbon to 71.1% oxygen, then it doesn't really matter what the amounts are. When you compare them, when you get them to moles, it's all going to be a similar percentage. That's the whole purpose behind percent composition. So we sometimes will say assume a 100-gram sample, because then if it's 2.2% of 100, that's just 2.2 grams, okay? So when you're given percentages, we are just going to change them into gram amounts. So you don't have to do these questions this way, but this is a good way to organize your information. So you have a column for each of the elements. I just went in order that the question said. So it said hydrogen first, and then carbon, and then oxygen. So when you write your formula, you can do the same thing, like HCO. And again, they're going to be weird ones like this. They have more than 2 elements. These are all nonmetals. They're not going to follow the crisscross rule, any of that. So just go in order that you're given it. And it says 2.2% hydrogen. So we're going to do 2.2 grams. 26.7% carbon. 26.7 grams. 71.1%. Because no matter what the sample is, that would be the percentage of each element. So we're just going to say, okay, well, let's say we have 100, and then it's easy to just use the percent values. So these stars here, relate to this. So the molar mass or molecular weight, where do you find that? On the periodic table, okay? So hydrogen, carbon, oxygen. And when you do this, try to keep as many decimal places as you can, okay? So I'm not going to round the hydrogen this time. And then we're going to find moles. So this looks squished to me. If you need to rewrite it, sorry, you can. Okay, we are going to change the mass into mass into moles. And like I said, usually this is a perfect example. When you're given grams, change it into moles, and that would get you 3 marks here. Okay, so doing that, hopefully you're like mass over molar mass, like it's so molecular weight, it's so easy by the end. Maybe not today, maybe you didn't get a chance to do it, that's okay, all right? So when you do this, depending on the kind of student you are, like if you like your notes to be sort of like all on one, like you want this chart to go on one line, then maybe you don't want to show like you're not going to write in here n equals and then show the math. It's up to you if you just write the answer, okay? It takes up a little bit more geography maybe on your paper if you show all of your work. One of the advantages to doing this chart, so we write the mass first because that's what you're given, right? This we get from the periodic table, but now when you've written it like this, now it's this divided by this gives you this. Okay, so it's a nice way to organize the information. So 2.2 divided by 1.008, 2.182. 26.7 divided by 12.01. 2.223 mole. 71.1 divided by 16. 4.443 mole. Okay, so then what we're going to do when you get to the mole ratio, we're going to get out your highlighter. Be a better highlighter than me. Or underline it or whatever, because this is really the newest part, okay? Everything else so far we've already done. We're going to take a look at the moles, and we are going to divide by the smallest mole amount. We want to get a formula, a chemical formula. So like CO2, H2O, whatever, none of those have decimals, right? But when you have a mole amount, it's perfectly reasonable to get decimals. So what we need to do is find out what the mole ratio is. So we are trying to find how are these things related to each other. So you pick the smallest one because we want the most reduced, and we don't want to go below 1. You need a whole number, okay? So this is the smallest. So every single mole amount, we're going to divide by 2.182. Why 2.182? It's the smallest. Smaller than this, smaller than that. Yeah. Yep, sorry. Thank you. Okay, so 2.182 divided by 2.182 is 1. So how many hydrogen atoms are in our simplest formula? 1, okay? Now, when we divide these two, we get 1.02. Okay? We can't have 1.02 of an atom, but what's that really close to? 1. Or what we're doing is trying to compare this to this. These numbers look really close. Okay, it's probably 1 to 1. And then when you look at this one, you can think 4 divided by 2, what am I probably going to get? 2. You get 2.04. That is very close to 2. Okay, please don't do all this work and then forget one final step, okay? Because you want to state what the formula is. Somewhere you can put, I just didn't want to write really low. You can put it wherever you want. Chemists are lazy. You can call this EF. How many hydrogens? I'm going to write 1 just to emphasize. How many carbons? 1. How many oxygens? 2. By default, this should be the most reduced, so just give it a check. Can you divide those numbers by the same thing? No, it's the most reduced. Okay, so this, you can just round, like follow the math rules, 0.1, 0.2, 0.3, 0.4, round down, 0.6, 0.7, 0.8, 0.9, round up. But there's always a trick, right? What happens when it's 0.5? Okay? Yes. You'll see. We don't know, so what we're going to do is try to make it as quantitative as possible. So I'm just going to randomly make something up. You guys have lots of space on this, right? Yeah? Okay. So pretend like I did the whole chart. I got to the mole ratio line. Only the mole ratio line. You can have 0.5 grams, you can have 0.5 moles, but when you get to the mole ratio line, which is the one that you're going to use to say how many atoms, that's where you have to check, okay? So what do we do? And again, we want this to be quantitative. We want it to be universal. If you're a chemist in this lab doing something, it's going to give you the same results somewhere else. Formulas for compounds are supposed to be pure substances, right? They're supposed to be the same everywhere. So the best thing that we can do is change this in the most simple way to a whole number. What do you multiply by? 2. Okay? If I multiply this by 2, that gives me 5. Actually, I think it's good. But what you do to one is math, right? You gotta do to it all. Times 2. Times 2. Are these still the simplest? Yes, you can't divide 2, 4, and 5 by the same thing. But now we haven't guessed. Do we round up? Do we round down? Please don't think that every single question is going to be like this. This is very rare, okay? But I think there's one on the review for sure. I forget about the homework. There's always one sneaked in there, but it's not like every single question is going to be like this. And it's only in the very last line. The mass can be 0.5, the moles can be 0.5. It's the mole ratio line at the very, very end, okay? So A is 2, B is 4, C is 5. You know what? Even write it down. Rare. Yes. No, because you want it to be simple, so always do 2. If you did 4, then what would happen is your numbers would all be, like, could be reduced, so you'd have to reduce it again, which is fine. Yes. It's the one right after, so you can just do 2.2 or think of it like 2.3. If it's one like 2.45, that is incredibly ruthless, and I wouldn't give you those. You'd probably have to do experiment like we're going to do today. So just look at the one right beside it, okay? Right after the decimal. Usually it's really obvious. Usually it's numbers like this. Okay, that obviously rounds to 3 or something like this. Okay, that obviously, like usually it's really straightforward. Or the one in the review is aluminum oxide. So when you do it, if you forget to do this, you don't get what you would predict with the crisscross rule. And then when you fix it, you do. So you're kind of like, oh yeah, I know this, right? So you can figure it out. Okay, so mass to moles, we already did that. Just divide by the smallest one. What you do to one, you do to the other. And then just maybe, you have to check for this. Okay, other questions you can do with empirical formulas are something like this. Which of the following are empirical formulas? So again, we're looking for, are they reduced? So C6H6, are we able to divide that by something? Yes, right? They're both 6. They can both be divided by 6. So I forget if there are questions like, make it an empirical formula, so you would have to write C1H1, or CH is fine. I can't remember. There's definitely a question like this in their homework. Is CH4 an empirical formula? Is it the most reduced? Yep, you can't divide 1 by 4 or 4 by 2, whatever. C5H10O5. So again, if you're a biologist, that is ribose sugar. So ribose is a 5-carbon sugar. It's very big. And so the molecular formula, the actual number of atoms, is C5H10O5. But in an empirical formula way, if you were going to do the most reduced, which doesn't often work for covalent, that's why we don't reduce them, then this should be C1H2O1, right? You can divide by 5. Same thing with this one. You can divide by 6. This happens to be glucose. So now this is a 6-member ring. Okay, so how do you figure out actually how many atoms there are without doing an experiment? Then you're going to do molecular formula. So the actual number of atoms in each element in a molecule. So again, usually reserved for covalent compounds. So there are compounds that can have the same empirical formula. However, they don't have the same actual number of atoms in a real way, especially biological ones. So then we need, if we're trying to switch to quantitative, how can we quantitatively deal with that? So sometimes the question will be like, part A, these are the amounts, find the empirical formula. Part B, blah, 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 molecular formula. So in order to do molecular, you have to have empirical formula first. So that's one thing you have to be given. And then, so depending on the question, like this example, it already gives it to you, and some of the homework will be like that, but then sometimes you might find it first and then do part B. And you need so you must be given, like it has to be right in the question. The actual molecular weight or the actual molar mass is, again, you could certainly determine it by experiment, but not when you're writing a test, obviously. Okay? So if the empirical formula of ribose is CH2O, okay, so we're given that. There's our number 1. And its actual molecular weight, there it is, number 2. What is the molecular formula of ribose? And this, doing the molecular formula is actually pretty straightforward. And if you are the kind of person who likes can easily sort of see relationships between numbers, then you actually maybe need to do very little math here, but it's always good to show it, okay? So in order to compare, we need to compare things that are the same. So we have the molecular weight, the actual molecular weight, and we have the empirical formula, but we don't know how much the empirical formula is, how much it weighs. So first you find that. That is not how you spell find. Okay, so like I said in the first lesson, you're going to do this molecular weight molar mass so many times. So you decide for yourself how much work you need to show, okay? So 1 carbon, 2 hydrogens, and 1 oxygen. Show all my work. So again, maybe you are good at this. Are 150 and 30 related? Can you get to 150 using 30? Yeah. You just multiply by 5, right? So if you do this and there is not a relationship with that number, then go back and fix it. Okay, you've made a mistake. Check your math again. You can always, if you're not good at that, always what you can do is divide. And remember, we want to get a whole number. So if you do 30 divided by 150, you're not going to get a whole number. So then that's your clue. Oh yeah, I got to go backwards. I got to do it the other way. 150 divided by 30. Ratio of, the ratio between. When you do something like this, they have to be the same. That's why we had to find the molecular weight. Okay, so if you have been trying to analyze your units every time, then when you do this, subdividing, they have to be the same, right? To cross out. So we want them to cross out. There's no units when you do like CO2, right? And then, so you get 4.99567. So really, what's that really close to? 5. Okay, so usually it's really obvious. That 0.5 thing is very, very rare. Okay, so again, please don't do all this work and then just stop here. You want to actually write the formula. Okay. So you multiply all the subscripts. What you do to one, you do to them all in the empirical formula by the ratio. So again, you might just show your answer here, or maybe you want to show your work. So now molecular formula is no longer going to be the most reduced. So again, this homework is listed and the solutions are on D2L, and I've split it apart into just empirical and then just molecular. Or maybe these ones you have to do empirical first, but if they are split.